Welcome back to Tailored Materials and Surfaces. We're going to think about how to connect something to the surface now. So if we imagine we're going to do some kind of coating procedure, we've got our coating atom, or we've got our, try and look at this, our surface atom, let's call this S. That's some kind of surface atom. And what we want to do is connect it via some kind of connector, and we don't know what those are, so let's call them X, X and something. So, and then we want to go to whatever we're going to have on the end. So this is what our goal is today. We would like to connect something to a surface that already exists. So this could be some metal, it could be an inorganic material, so it could be a ceramic, it could also be a polymer. But the goal is to have a chemical bond all the way through. The first molecule of interest here is a silane, which in this case is a chlorosilane. It's got one chlorine on it, two groups, and one group that's different. Why that is will be apparent in a moment. What we expect to happen is that our silane chemical, an organic chemical, will tend to go towards a piece of glass, effectively, a silicon dioxide type chemistry, if it can, because the silicon dioxide type chemistry is very low in energy, and so it's stable. So how can we get there in a little bit, but obviously achieve the thing that we want to achieve? So this is our possible reaction. We've got lone pair from a hydroxide bond from our surface. This is just a surface atom. The lone pair can attack the silicon, and it can kick out a chloride ion as Cl-. That will obviously then, let's resolve that. So let's get rid of this and make a bond. That will obviously make the oxygen have too many bonds, and it will also have a positive charge, which means it can steal these electrons from the hydrogen, giving out an H+. So we end up effectively with hydrogen chloride. So let's put that on, HCl plus our surface bound silane. So that will be our possible solution. But let's have a think about what this reaction actually is then. So we've got our hydroxide. It's going to attack. It's going to attack in here, and the chloride is going to leave. What can possibly happen? Well, we've got a silicon and not a carbon. So typically we would normally expect if it was a carbon, it would have to be an SN2 type attack or an SN1, probably an SN2. So it should attack from behind. And because it's a silicon, we can have a slight difference. We can break the number of bonds that we should have. So we could have a 5-membered silicon for a short time. That is okay, because silicon is a period down from carbon. It's got more orbitals, so it can have more possibilities, and 5 bonds is entirely possible. So now let's think about what could possibly be on the side here. We could have a big organic group, for example, but the problem there is that when we bring another one up to this neighboring hydroxide group, it's not even the neighboring one, but if we bring one up to the neighboring hydroxide group, we may end up with problems. They may not fit, and then we may have to ignore one of the groups in between, and that's not ideal if we want to attach to as much of the surface as possible. Whoops, that's weird. So what we can do is we can make these very small. We can make these methyl groups or hydrogens. Hydrogens aren't so good because they can hydrolyze off, particularly in the acid conditions that we have with hydrogen chloride in there. So we could put a methyl group on there and make it relatively small. Or we could try to attach this one to the next one to make a layer across the surface, which heals quite a lot of other So inaccuracies with our surface, it may not have a hydroxide every one. We may struggle to get enough hydroxides on our surface, and if we allow it to link sideways, then that will help to be able to gain a completely covered surface with a known amount of outside groups that we can do things with. So we could start with, or we could end up with this. This could be our goal, that we have an oxygen bound in between to generate a completely cross-linked surface layer with our random groups or our chosen connecting groups on the outside, which we'll come to shortly. And then we can think about doing this connection. The problem, of course, is that if we have chlorides here, this oxygen has to come from somewhere, so we have to add some water. The water can react to form hydrogen chloride, and it forms a hydroxide here, which can then attack the next one. But of course, that's a little bit uncontrolled. We need to deal with the water. Silyl chlorides react very quickly with water, and so maybe we should start with something a little bit less reactive, that's a little bit slower, and that doesn't give out hydrogen chloride, because if we imagine this surface is aluminium, for example, the hydrogen chloride is going to corrode our surface. If it's aluminium oxide, if it's zinc, there are a lot of compounds that it will corrode. If we put it into paint and we sell it to consumers, it will make hydrogen chloride, maybe pop the lid off, and when the consumer opens the lid, they'll get a whole lungful of hydrogen chloride. It's not the best thing to do. So there are alternatives that we can think of that contain less groups that fall off, or less bad groups that fall off, and maybe aren't so volatile themselves. Because if we have our organic group, a silicon group, and 3 chlorines, it's likely to be very small and volatile. These silyl chlorides are not very polar, which tends to make them reasonably volatile, and so they'll tend to get lost from your composition. It doesn't mean you can't do it in lab. It doesn't mean you can't do it in a technical coating kind of environment, but it does make it more difficult to deal with, and it makes it more difficult to choose substrates. It's obviously fine on glass, because hydrochloric acid doesn't attack glass, but it limits the substrate that we can use, and it limits the conditions that we can use. So this is the trimethoxysilyl whatever compound of R, and this is one of the most important coating materials that we can think of. Trimethoxysilyl or triethoxysilyl are very common. We could use dimethyl methoxysilyl, but this bond is what I'm interested in right now, the silicon oxygen carbon bond. Silicon oxygen carbon is unusual because it doesn't behave like an ether. You can see if this was carbon, oxygen, carbon, it would be an ether. And ethers, as you know, probably some of you, ethers are relatively stable. They're difficult to attack by organic chemistry. You can leave them lying around. Things happen to them. So they react with oxygen slowly to form peroxides, and that's very bad. But they don't react with water very much. What we want is something that behaves like the chloride, that will leave via some kind of nucleophilic attack, ideally SN1, but also SN2 would do. And we would like it to leave from the attack from an OH bond. So that's our goal. And this is actually the case here. This ether behaves much more like an ester bond does in a carbon than it does in an ether bond in a carbon. And that's to do with how the silicon and the carbon have their electrons, and how many orbitals the silicon can have to share its electrons with. Whoops, hang on, let me turn this a little bit that way. Yeah, that's better. So let us start by protonating this oxygen here with a proton, obviously, to make it a better leaving group. That's a good first step. And now our water can come along and replace the alcohol in a very similar way as it would do on an ester. We don't have the double bond O to bounce some electrons into, but the silicon, as I mentioned before, can hold 5 bonds for a short time, so it can attach first and then the other one leave, which makes it much more likely to happen. So in this case, we've got an acid catalyzed, effectively an acid catalyzed swap to an OH. This hydrogen will drop back off again, and we will end up back to the methanol. In that case, we'll end up with our proton back to attack another one, but we could do it base catalyzed. Let's do that next. So if it's base catalyzed, much the same as in esters, exactly the same in fact as in esters, we can attack directly to the silicon. We can make our new bond, our OH, and we can lose then the anion of the alcohol. Sorry, I keep drawing. So we will end up in either case with the same product, which I'll draw. What was the point of going here? Well, this is a lot less sterically hindered than the methoxy group. There's a lot more space here. We can bring in our surface and we can cause this to leave. That's good. It's also slightly more reactive. And if we want to have access to the other side of this bond to make our cross-linking process, we need to get to here first so that we can access the next one, so that this lone pair can attack the next one and lose this, because we're not going to be able to break this bond very easily. It's the bond in an alcohol. Those don't get broken nearly as easily as the bond between an alcohol and an ester, and between an alcohol and an acid in an ester. So theoretically we can make the trial. It's not very likely. What we usually do is we replace some of them and not all of them, and then they start to react with each other and with the surface. It's a much more ugly reaction than you would expect if you do this first. In reality, it starts to react with itself immediately to form oligomers, which is a bad thing about having multiple bonds. If we only have one, then it can't do that. So if I have two methyl groups and an R group, and I make this, then the most that I can make is the dimer, and the dimer can't do anything. Whereas if I make a large chunk of polymer, it will sit around in the solution and reduce my the life of my polymer, and it will do bad things. It will stick to stuff, it will make it chunky, so it will cause problems. On the other hand, if we can cross-link across our surface, then we can equal out some of the missing bonds that we would otherwise have a problem with. We can make it nicer. So it depends. It depends what our substrate is, whether we want to connect these two or not, and it depends how strongly we want to bind to it as well. So now I would like to think about what this R is. So we've now attached it to the surface. It's aluminium in this case, so we've used an alcohol, and we want to know what can our R group be and what is it usefully. So ideally the R group will now attach to something else, to our paint, to our coating, to biomolecules, whatever we want to attach to this surface. And it will also not break in the conditions of coating. Obviously, if we have something that's really reactive to water, like a chloride, it's going to have already reacted. If we have something that's very reactive to acid, then we'll have a problem if we use the chloride, because hydrogen chloride is released when we do the reaction. So we're limited to a certain extent with what we can do, but it's not a very harsh reaction. This reaction goes at room temperature. This reaction, so to completion, takes a higher temperature. These side bonds, if we think of them as side bonds, if we think of this one's happening first, then these will take longer. They may take a slightly higher temperature to finish completely, but we don't have very many chemicals in there. So we are relatively free, and that's why this is a common reaction. We're relatively free as to what we can have on here. There aren't very many sensible options, however. So one of the things that you'll be familiar with probably is if we want to attach a polymer directly and we're doing chain reaction, then we could have a double bond on there. We could have a double bond on there and we could use it to attach to a polyethylene while we make it. But we could also have a double bond on there and use it to attach to the cross-linker in polyurethane. If we take polyurethane and you buy it, then it's usually cross-linked. It's usually, the polyurethane is already a chain and it's cross-linked via a free radical mechanism using styrene as the intermediate. So we could put styrene on here, a styrol group. So we could have, so now we've got our double bond in our surface. A radical can come along from our reaction or our polymer, and it can add, let's add it like that, it can add to the double bond, making it part of the surface. Obviously we then end up with another radical. Eventually they will get all mopped up, but that's how radical reactions work. You end up with a few radicals left over. So we're going to then attach our polymer that's growing directly to the surface via a chemical bond through this silicon. Another big family are the epoxides. So we can have an epoxy adhesive, and an epoxy adhesive is typically the reaction of an amide and an epoxy. This is an epoxy, this triangular group, and it reacts by being attacked from behind in a ring opening reaction. It's effectively an SN2 ring opening reaction, which has more energy because the ring is very strained. It's only a triangular ring. So we can have whatever we want attacking here. Typically in an epoxy adhesive or an epoxy paint, we would have an amide. So we would have an amine, sorry, on the end here. So we will have some kind of compound that will attack. But if we have a nitrogen, if we have the amine group, then we could make our silane much more stable if we put the amine group on the silane and use the epoxide in the solution. Because epoxides, while they are reasonably stable, they're not as stable as amines. In an epoxy adhesive, typically you would have a diamine and a diepoxide so that you can keep them separately, mix them together, and then they connect by the same ring opening reaction. But now if we've got some amines on our surface, they can also get involved. So this one can attack this epoxy group, then we've got a little bit of a linker, and then we've got the other epoxy group which can attach to a diamine, and then it can go on and on and on and make a giant polymer, which is what epoxides are, or epoxy adhesives or epoxy paints end up being. The good thing about having an amino functionalized silicon or silane that we can use to attach to our surface is that we can also use it to attach to biology things, because the biology group would then be a typical amide bond where we can attach this to a protein via the acid end. So the acid will then attach to this amine and it will attach in just the normal way that we would normally expect. So what else could we put on here? We could make this chain just very, very long, which would allow it to interpenetrate with a polymer and hold it on by just non-polar forces. We could also put a sulfur group on there. So, oops, I've run out of pens. We could also put a sulfur group on there. That would be a thiol maybe. And we could then cross-link that with proteins in a cysteine bond type of situation. So we'll end up with a sulfur-sulfur bridge. If we do that, we can also do that with rubber. So rubber is typically vulcanized with sulfur, and the end bond is a sulfur-sulfur bond. We could also use this thiol to attach to other things. And the good thing about the thiol is it won't interact with this other reaction. It's kind of stinky, but it's not going to react in the other reaction. And this will also attach to other things that are not organic if we want to. So we can attach to biology, we can attach to organic materials in that way. The other thing that I forgot to mention was how long is this chain? We can obviously have a variously long chain here, and the longer it is, the more compatible it is with an organic solvent, because these things are quite polar. So if we look at a silane, if we look at a silane that looks like this, Si with 2 methyl groups on it, and let's have OHs on there, OH, 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 then we'll end up with something that looks very familiar to you. It should do. It looks very much like a fatty acid, except it's got a silicon in it instead of a carbon. And these are obviously OHs instead of double bond O's, but it will behave very much like a fatty acid, and so it's going to have a polar end and a non-polar end. It's going to head for an interface. That's good because it will go and stick to our surface automatically with the correct way down, as long as this is polar, our surface, and if it's aluminium oxide it will be polar, so it's going to orientate itself correctly. It will help our polymer to mix with other things, so if we want to have it in there, we will have problems. If we don't want to have it in there, for example, we might have problems with water on the surface of our aluminium getting into our paint and or interfering with contact between the paint and the surface. But if we have something that's like a soap, it will allow that to dissolve into the solvent of the paint. So these polar, non-polar molecules that will then go away and attach to the surface can be useful for all kinds of things. So alternative to silanes, what we could do is form a metal ligament bond to a metal site. So instead of going over an oxygen hydrogen bond, we're going to go directly to the metal. This is an example. So this is a fatty acid, and if we deprotonate the fatty acid, so it does require somewhere to put that proton, we will then end up with the acid anion. So this is negatively charged, and this can attach to things that are let's have a calcium ion, calcium 2+. This can attach to calcium ions, for example, and form a metal ligand interaction. It forms 2. You can see that after on one line from each oxygen, because the calcium has its orbitals in these directions. That makes the bond particularly strong, even though they're not full bonds. So because we've got more than one of them, it's harder for it to let go. We can see an example of this in the very nasty gunk that you get near your wash basin, near the sink, near the rim, wherever the water normally reaches. It's when soap, which is typically a fatty acid, soap, particularly hard like block soap, interacts with calcium ions in the water, not gallium ions, but calcium ions in the water, and forms a solid material. In that case, it's got more than one of these soaps on it, but obviously if it was a calcium carbonate or something else, or a bone, calcium phosphate, it would not be available from the bottom side, and so it would only be able to connect to one, or maybe two, probably only one. Can we think of some other chemicals that do the same thing? Alternatively, we could take a phosphate, or in this case a phosphate ester, so the ester of phosphoric acid. We can also deprotonate that, or we can make it in a deprotonated state and take the anion and interact it with a metal, Me4+. So it's very much the same. We've got a sort of square of bonds in much the same shape, and we've got a negative charge that's being shared between two oxygens which are both attaching to the same metal typically. You can see in both cases there are oxygen atoms attaching to the metal. If we have a small metal, a metal with very relatively small orbitals, they will have a good overlap with the oxygen atoms, And in chemistry, we call that hard and hard because they're small. We've got tight control over the electrons, and because the orbitals are both small, there's a good orbital overlap, and so the bonding is comparatively good. If we take a bigger atom, like copper or gold, for example, it is more difficult for it to interact with oxygen because it's got big orbitals and the oxygen has got small orbitals, so the donation from the small orbitals into the big orbitals has a bad overlap. So we could get much better interaction if we find an atom that is similar but bigger, and that would be sulfur. Sulfur is the next atom down in the periodic table from oxygen. In this case, we've got a thiol, the sulfur equivalent of an alcohol, which is interacting with gold, which is a larger atom. It's a heavier atom, but it's got bigger orbitals. It doesn't interact very well with oxygen, but it interacts very well with sulfur. The exact nature of the bond is a little bit more difficult to work out what's going on. It's somewhat unclear, because typically we would expect the gold to give electrons to the sulfur, and then we'd have a problem here. What is unclear is whether this hydrogen leaves as a proton or not, but there is some kind of bond between the gold and the sulfur, and it's not as strong as a full bond, but it's a lot stronger than just sticking on the surface. If we take a disulfide, which is sulfur that's already formed a sulfur bridge to another one, we can also get it to attach to the surface, and it appears to be two bonds, but we can't tell which is exactly happening. But in this case, what is important to us when we're thinking about which molecules will we attach to surfaces, if we've got gold, we are limited to carbon and sulfur. Most things won't attach, or we can attach a metal to it directly. If we've got something that is small, it will tend to attach to oxygen, so we can use oxygen connected organic materials such as carboxylic acids. And if we have the facility for making a hydroxide bond on the surface, we can use a silane. So now we've got a small but fairly powerful toolkit which we can use because we can do chemistry on the rest of the molecule. We can use to then attach whatever we want to the outside of a surface. Ideally using the lowest complexity, or the weakest conditions possible, so that we can use it in paints or in coatings where other things are going on, so we can't do very much chemistry, we can't heat it up very much, we can't use very strong reagents. So ideally we would have it binding on its own and it not doing too much to anything else, because that will make everything far too complicated. Particularly if we want to involve biomolecules as well, because then they tend to break down as soon as we put strong reagents in there. Okay, so we'll stop for today and get on to another theme next time. Okay, with you next time.